10.3, using permutations and combinations. In the earlier section, we talked about Alan, Bill, Kathy, David, and Evelyn. And we considered two questions. How many ways can all the club members arrange themselves in a row for a photograph? And how many ways can the club elect a president, a secretary, and a treasurer if no one can hold more than one office? Now, to answer the first question, we did it by using factorial. So if we have 5 members, and we want to look at how many ways all the club members can arrange themselves in a row for a photograph, we did it by having 5 positions for the photograph. And there's 5 possible ways for the first position, 4 people for the second position, 3 people for the third position, 2 people for the second position, and only 1 possible way to have a person for the last position, which is simply 5 factorial, which is equal to 120. Now, how many ways can the club elect a president, a secretary, and a treasurer if no one can hold more than one office? And we could do this using a tree diagram because it's a multi-part task. Another way we can think of it is how many arrangements are there of 5 things taken 3 at a time? In the context of counting problems, arrangements are called permutations. The number of permutations of n distinct things taken r at a time is denoted as follows. N distinct things taken at r time. Taken r at a time. And the number of objects being arranged cannot exceed the total number available. So we assume that r is less than or equal to n. Applying the fundamental counting principle, it gives us n minus 1, n minus 2, n minus r minus 1. The first factor is n minus 0, the second is n minus 1, the third is n minus 2, and so on. The rth factor, the last one in the product, will be the one with r minus 1, subtracted from n, as shown above. We can express permutations in general in terms of factorials to obtain a formula. And that formula is n factorial over n minus r factorial. And this is a very important formula to memorize for this class. So memorize this for permutations. So we could do a couple of examples. So for distinct items taken 2 at a time, because this is n, which is distinct items, and this is r. And from our formula, we have 4 factorial over 4 minus 2 factorial, which gives us 4 times 3 times 2 factorial over 2 factorial. These cancel out and leaves us with 12. What about 8 distinct things taken 5 at a time? We can do 8 factorial over 8 minus 5 factorial, which leaves us with 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. It's going to leave us with 6,720. Now, what about 5 distinct things taken 5 at a time? Well, this is simply just going to be 5 factorial. Because if we work out the formula, we're going to be left with 5 factorial over 0 factorial. And we know 0 factorial is always going to be equal to 1. So this is just 5 factorial over 1, which is equal to 5 factorial, which is equal to 120. So for our problem solving strategy, this is the 2 things that we need to know. Permutations in general can be used anytime we need to know the number of arrangements of R objects that can be selected from a collection of N objects. The word arrangement implies an ordering. So we use permutations only in cases that satisfy these conditions. Repetitions are not allowed and that the order is important. And so we can have another example. How many non-repeating 3-digit numbers can be written using only the digits 3, 4, 5, 6, 7, 8? We have 1, 2, 3, 4, 5, 6 distinct objects. And we want to take 3 at a time for 3-digit numbers. So 3 is equal to R. And repetitions are not allowed since the number are to be non-repeating. For example, 448 is not acceptable. And order is important. So 476 and 746 are not the same thing. They're distinct. So we use permutations to determine the total number of ways. So we have 6 distinct things, taken 3 at a time. And we know from our formula, we're going to have 6 factorial over 6 minus 3 factorial. It's going to be these cancel out, and we are left with 120 ways. Now we look at combinations. Recall that the club N, which is equal to Alan, Bill, Kathy, David, and Evelyn, could elect 3 officers in 5 things taken in 3 different ways, which is equal to 60 different ways. With 3-member committees, on the other hand, order is not important. The committees BDE and EBD are not different from each other. The possible number of committees is not the number of arrangements of size 3. Rather, it is the number of subsets of size 3. And if we remember in the study of sets, a set is a collection of group or things, commonly designated using a list within braces. And we have been designating the club N is equal to A, B, C, D, E. The order of listing of the members is unimportant. So D, B, A, E, C is the same club. A subset of a set is a collection of the same members. It may be all the members of the original set, or even none of them, or anywhere in between. Such subsets are combinations. So let me repeat that for you. A subset of a set is a collection of the sum of some of the members. It may be all of the members of the original set, or even none of them, or anywhere in between. And subsets are combinations. The number of combinations of n things taken R at a time That is, the number of size R subsets given a set of size n is written as NCR. These are n things available, and we're choosing R of them, so we can read n choose R. And so in a permutation of 5p3, this would be 60. But in a combination, order isn't important. So ABC is the same as CBA. So we don't include those subsets. And so the only subsets that would be in a combination would be 10 of them. And I'm going to go into further detail into how we get 10. The formula for combination is going to be the permutation over R factorial. And so we get n factorial over R factorial over n minus R factorial. And let's do some examples. So 9 choose 7 is going to be, remember, the permutation of n choose R over R factorial. And so we get np7 over 7 factorial. And when we simplify that, it's going to be n factorial over R factorial n minus R factorial, which is going to be equal to 9 factorial over 7 factorial 9 minus 7 factorial. And that's going to be 9 times 8 times 7 factorial over 7 factorial times 2 factorial. The 7's cancel out. It's going to be 72 over 2 times 1. It's going to be 36. And so we use combinations in the following cases. The key difference between permutation is this. In combinations, order is not important. So when the order is not important, we use combinations, and they're only applied in these situations. So repetitions are not allowed and order is not important. Compared to permutations where order is important. And we're going to look at a lot more examples. Find the number of different subsets of size 2 in the set A, B, C, D, and list them. So different subsets of size 2 in the set A, B, C, D. So we know that repetitions are not allowed. And we know that they have to be different. So the order, it's not important. So we use a combination for this. We have 4 elements. Choose 2. It's going to be 4 factorial over 2 factorial times 4 minus 2 factorial. So it's going to be 4 times 3 times 2 factorial over 2 factorial. These cancel out. And then 4 minus 2 factorial is going to be 2 factorial. 4 times 3, which is going to be 12, over 2, which is going to be 6. Another example is a possible number of poker hands. So a common form of poker involves hands, which are a set of 5 cards each dealt from a standard deck consisting of 52 different cards. How many different 5-card hands are possible? The reason we use combination and not permutation in this is because the order is not important. So say if we had the hand an ace, 2, 5, 6, 3. That's the same thing as 3, 5, 6, 2, ace. In terms of poker, the order is not important. These are both the same hand. So we use combination in this. So we have 52 distinct cards, and we want to choose 5 of them. So it's going to be 52 factorial over 5 factorial times 52 minus 5 factorial. It's going to be 52 factorial over 5 factorial times 47 factorial. And the end result is going to be 2,598,960. So that is permutations versus combinations.